We're going to stick to the line that says kinematics and start there, and move down for these first couple of videos because that's kind of where you guys are starting in class. So we have this symbol delta. That's what this triangle is called, um, which is a symbol to represent a change in a quantity. Um, if you've ever heard of a derivative, which I know this is algebra-based physics, so maybe not for some of you, but those of you who have, they're kind of related, um, but slightly different, and we might touch on that a bit later. So anyways, we know that our x variable is a coordinate. I presume everyone's familiar with that, right? Just like a position graph, right? So we are going to have a little bit of an x-axis right here. Bear with me, this whiteboard is a little finicky with this pen I'm using. Let's say we have a little x-axis and we have 2 points on this axis. We have x initial. This little I stands for initial, and it's just the starting value of that variable. And this little f means final, initial, and final. And our equation sheet gives us that delta x is equal to x final minus x initial. So the difference in our final x value from our initial x value. So if there's a world where this is actually our origin, right? And this is actually 0, 0. And so then our x is equal to 0. Then this equation simplifies down to delta x is equal to x final. So in that case, you could just ignore the x initial, or you could plug in 0, whatever makes sense to you. In a world where x initial is equal to literally any other number, or just any number generally, you can take the value of your x final, say that's 5, and this is 0. In that case, your delta x would be 5 minus 0, which obviously equals 5. So your change, right, your delta in your x coordinate is the difference in your final x coordinate and your initial x coordinate, or 5 minus 0. You changed 5x units. You moved 5x units. Your value of x changed by 5. In that, also, similarly, our equation sheet will also be referring to the quantity delta t, which is sort of the same format, but we're changing out those variables, right? And now instead of our x variable, we're going to talk about t, which is time. This. And again, we have that final and initial. This is called, you see how they're written slightly below our variables? These are called subscripts. Most of us, we've probably seen these in class at this point, but just for review. And also, the good thing about these videos is they'll be available to you anytime. You can rewatch them at any time, and get sort of a reminder. I'm going to try and keep them quick, so that they're easy to sift through and you don't have to like go through a big long video. So you can get these quick reminders and kind of skip through as needed. All right. So yeah, now we understand this quantity is a change in a coordinate. This can be any letter because it is just a variable. It could be in the y direction, it could be in the z direction, it could be just the letter a, like the change in just some variable and its value. This formula of the change in a variable equals the variable's final value minus its initial value will stay constant. Next, we're going to touch sort of on these equations here, the v with the little line over it and the a with the little line over it, which are called v bar and a bar respectively. And I'll just go over here. Actually, I'm going to move this up a little bit. Make sure you have, let's say v bar That's this guy. And I just want to make it clear when I'm saying V bar, this is again what these videos are trying to aim to do. Sometimes in class, the professor won't necessarily remember to just mention, or maybe they say it really quickly and you don't catch it. This line is a bar. That's what we say, V bar, like literally the word bar. And that equates, that symbol of the line represents an average value. So this V is a velocity in this case, right? Speed, meters per second. So this is an average velocity. So V bar is an average velocity. Hopefully that all makes sense. And then we are given the equation for V bar. It has all these variables which we've seen before in our equations that we were just working with. And just for the sake of completeness, we also are given a very similar looking equation with slightly different variables. It's not supposed to be a V. In a minute here, I'm going to discuss sort of how this A and this V are related. A being acceleration. I'm not sure if I said that yet. You can kind of get a sneak peek of my planning on the right there. But yeah, so let's break down these sort of formulas right here real quick. They're also given to equate to delta x, which is that quantity we discussed already, and delta t, and this is given as delta v over delta t, just straight from the equation sheet, right there. These quantities, these delta x over delta t and delta v over delta t, these are rates of change, or slopes, which, because rates of change might just have jogged your memory, these are similar to slopes, right? I want similar to y equals mx plus b, but we want the m in particular. So we're gonna relate this notion to slopes. And now I'm gonna give you a little sidebar here, and we're gonna talk about a little bit of calculus to get an understanding of what all these deltas and all these changes in values actually mean when it comes to physics, right? You've seen slopes on graphs in your algebra classes before, but what do these slopes mean in practice? They actually have substantial physical implications. So we're going to start with what's called a position function, our x of t right here. This format of, if you haven't seen it before or just not in a long time, f of t, this is function notation, a function of t, right? So the f of t in this case, the x of t, is going to be our position function. And this graph shows us the position of, say, an object versus time. So as time progresses, where is this object in terms of its x-coordinate? As we can see, starting at time 0, we're at a pretty high x-coordinate. We stay at that x-coordinate, we start to drop down. We have a negative slope at point P, as illustrated by this dotted line here. And then as you get to point Q, that slope gets less intensely steep and goes to 0, right? You see this line that's at point Q, touching point Q is 0. That's the slope at point Q. Then we go back to a positive slope and go back up the curve. You see this dotted line is representing a positive slope over here. At first, we have, this is about 0. The change, remember we're working with the change in x over the change in time. So the slope of this can also be represented by what's called a derivative, dx over dt, which I hinted at earlier. The d and the delta are slightly different. We were sticking to using the delta in class for the most part, given that this is 107. But for the purposes of this explanation, just recognize that this is a derivative, and the way that we relate position to velocity to acceleration is through taking derivatives, which adds a dimension basically to these functions. So when you have just an x, you have a measure of meters. When you have a measure of velocity, you have a measure of meters per second. And when you have a measure of acceleration, the unit is meters per second squared. Right? So x of t is in meters, v of t is in meters per second, and a of t is in meters per second squared. You could think of this also, just for the sake of seeing what I'm trying to get at. If you have a number raised to the 0th power, that's the same as equal to 1. So s to the 0 is equal to 1, just side note. So this goes to 1, right? So just so like we understand, I didn't change the value of meters, but so that you can see, this is the same as writing seconds to the 1 in the bottom there. And so now you can see that as I progress from the position, I have meters over seconds to the 0. And then I take the derivative, which I'm going to get into how these graphs, why they look how they look. I'll explain that in a second. But you can see that you take the derivative of the x of t function, v of t is equal to the derivative of the x of t function, dx dt, the change in x over the change in t at any given time value. So I take the derivative of the point p. It's quite negative, so that is my most negative point. That is the most steep that slope gets negatively. So that's my most negative point p right there. So you can see that the velocity is related to the position by taking the derivative of that position function. And when I do that, it actually adds a dimension. So if you think of like 1 dimension, 2 dimension, 3 dimension, right? You're raising this to a certain degree. You can think of them like that. You go from 0, you have to go to the first power, then you have to go to the second power when you take the derivative again. If you kept going, it wouldn't make much physical sense at this point. In intro physics, honestly, yeah, it doesn't have much physical meaning. So we're going to kind of just stop at acceleration, but you can see that brings us s to the 2. We're relating all of our functions by taking derivatives and just adding sort of like a different dimension of evaluation. So point P has a slope that's quite negative. So point P is at the negative, or the velocity here is the derivative or the slope at point P, which is quite negative. So point P needs to be on the velocity graph. Point P needs to be quite negative. And then at point Q, we see that the slope is 0, so we have to increase our slope. Or we have to increase our curve rather back up to the value of 0 for v of t, because the derivative at point Q is 0, and that is the value v. And hopefully that makes sense from there. And then you can see going from v of t to a of t, which I guess I should be consistent here. Point P has a slope of 0. So I put that slope at point P of 0. When we take the derivative of v of t dv dt, that is our a of t value. If our slope at point P is 0, then our a of t at P needs to be 0. And then I can come to our point Q. This is my steepest point right here, where I have the most positive slope I'm going to have. My most positive point on my a of t graph is point Q. And then you can see that the slope is still positive, but less steep after point Q until you hit 0 again at the top of that curve. And so my value A of t is still positive until eventually it hits 0 at the top of that curve, and then it goes negative again. So as you can see, these are graphically related quantities if you apply some calculus. Again, that's just a little bit of a sidebar, but I think it's important to give some physical context because I know a lot of people in physics classes appreciate sort of a visual, and that's not always super accessible for some abstract stuff or like representing math. But in this case, it is if we just accept what a derivative is for now, and we can just sort of objectively look at these graphs and understand the relationships of slopes.